punctuation.
So a lot of virtual problems as well. So I totally understand.
Let's invoke something. Fortunately, the standard library already has a utility to do exactly this. But as we stare at std invoke, as we consider it through the lens of the single responsibility principle, we realize something. Std invoke doesn't have just one responsibility, it has two. It doesn't just invoke things, it also applies arguments thereinto. If we want to narrowly satisfy our requirement, we need to reformulate invoke so that it only admits nullery invocables. But in my software engineering career, I've noticed that one of the first requirements that slips is one of cardinality. You're assured there will only ever be exactly one of something, and then some number of weeks later, someone says, well, it can't be that hard for there to be n, can there? And so let's front run that. Let's invoke multiple things. Let's invoke several things. Let's extend invoke by writing invoke all, which admits an arbitrary number of invocables, invokes all of them, concatenates their return values, if any, into a tuple, and then returns that tuple. And here we see our insight vis-a-vis the single responsibility principle paying dividends. We don't have to look through our parameters trying to decide which are invocables and which are arguments that we should apply, because that application is someone else's problem. It's someone else's responsibility. Let's take invoke all and actually use it. Let's bring together two invocables, perhaps from distant parts of our system, and invoke them together. The first one, A, waits for 1 second and then prints A. The second, B, waits for 2 seconds and then prints B, and we invoke both of them with invoke all. And if we test our program by running it and wander away to get a coffee and come back, it looks like it worked. It printed A followed by B. But if we pay more careful attention as this program executes, there's a problem. The runtime of the program is 3 seconds. It's overwhelmingly likely this is not what the author of B expected, because they wanted to wait for 2 seconds, not 3. The problem is that invoke all sequences the invocations of A and B. What we're seeing here is a motivation for a move from the synchronous domain to the asynchronous domain. And fortunately, C++26 is bringing us the tools to do exactly that. It's bringing us std execution. We can just reach into std execution and we find std execution when all, which is the asynchronous analog of invoke all. But notice the change in abstraction here. We don't admit nullery invocables anymore, we admit senders, which are the asynchronous analog of a nullery invocable. But there's another change in abstraction here as well. Unlike invoke all, which performs the computation eagerly, when all simply returns a new sender, which lazily represents the computation that it would do. This laziness, of course, can't last forever. Sooner or later, someone is going to want to actually do something, and when they do, the asynchronous operation provided by when all looks like this. It starts, and in so doing, starts all of its children, allowing them to perhaps make forward progress in parallel. Then it fans them all in, waiting for each and every one to complete before it completes its overarching asynchronous execution. Armed with this, we can go and reformulate our example. Instead of having nullery invocables, we now have senders. We obtain those senders by composing an operation which waits for a certain number of seconds, and then an operation which runs immediately after the predecessor. The sender for A waits for 1 second and then prints A. The sender for B waits for 2 seconds and then prints B, and the output of this program is identical to the output of the example we just saw, except the runtime is 2 seconds and not 3, because A and B are allowed to make forward progress together. But we haven't exhausted the problem domain. There's one way in which invoke all and when all are deficient. They only admit a fixed number of children. You have to decide the number of children at compile time. What if I want to invoke a variable number of things? What if I don't want to fix the number of my children at compile time? I could turn, for example, to something like when all range, which accepts senders from a range rather than directly as a parameter. Something that leads to the following asynchronous execution, which looks identical to when all, except now we don't know the exact cardinality of our children. But there's a problem here. The problem is that when all range is not in P2300. We can't just upgrade to a C++26 standard library and start using it. We have to bear out one of the core promises of std execution. which is that it's not a closed set of asynchronous operations you can use without the possibility of extensibility, but rather that it is a generic framework in which you can implement arbitrary algorithms and arbitrary computations. But in order to do this, we need to first understand std execution, and fortunately I gave a 2-hour-long talk on that in Tel Aviv last year. Unfortunately, I can't assume everyone has seen that talk, nor can everyone leave and come back for me to continue in 2 hours. So let's do a brief recap of std execution. Let's anchor our analysis by staring at the synchronous function declaration that we all intuitively understand. But what do we understand looking at this, and why? Looking on the left-hand side, we understand the synchronous function returns exactly one integer. To rephrase this in language which is portable to the asynchronous domain, we know that foo represents a synchronous operation which, on completion, yields a single integer. Moving to the right-hand side of this declaration, we understand that this synchronous operation completes in exactly one way, with success transmitting one integer, because it can't propagate exceptions and thereby represent failure. We can take this information and we can represent it in std execution. We instantiate the std execution completion signatures template with function types representing each completion. This particular function type represents a completion wherein set value is sent reporting success, and it's contextualized with one integer. This is exactly the same form of completion we just saw in the synchronous domain. But returning to that synchronous function declaration, we can make it more complicated. We can make it able to complete in another way. We can simply eliminate that no except. Now this function has two semantically discriminated ways by which it can report its completion to its caller, to the person who, in our asynchronous parlance, initiated it. It can report a value, one integer, or it can report an error represented by an exception. We can take this information and represent it in the asynchronous domain as well. We can say that in addition to completing with set value of int, we also complete with set error of std exception putter. We asynchronously throw an exception. But std execution admits far more richness than we see in the synchronous domain, than we see from regular functions. For example, we have no need of extrinsic product types. We can simply just say as a first-class citizen that we yield multiple values when we complete. We don't need extrinsic sum types. We can simply say that our asynchronous operation completes in two ways rather than one. This newly added completion signature is a set value completion signature which sends nothing. It is the asynchronous analog of returning void. Perhaps more excitingly than that, though, asynchronous operations can complete in a third way that synchronous operations simply cannot. They can report to the person downstream from them that they simply stopped trying to make forward progress. They simply gave up for some reason. They thought the computation was defunct. They didn't succeed because they didn't actually perform the tasks they were initiated to do. But they didn't fail either because they didn't encounter some impediment to their forward progress. They simply stopped trying to make forward progress. But this is just how asynchronous operations report their completion. It does nothing to actually get us asynchronous execution. For that, as I talked about earlier, we need a sender. Of course, we can interrogate the sender to find out the ways it completes by instantiating the std execution completion signatures of t-type alias. We must also provide an environment, which is something we'll go over later, but for now we simply provide an empty one. But what lurks inside a sender? What makes it the asynchronous analog of a nullary invocable? For that, we have to look at its interface. It has a nested type alias, which simply exposes the fact that it is a sender. It's necessary to have this for the std execution sender concept to be satisfied. Then it has a static const eval member function get completion signatures, which is the way by which we publish the manners in which we complete asynchronously. Note that we receive ourself as a template parameter and also that environment we saw earlier. The reason we receive ourselves as a template parameter is so that it's not necessary for us to have an instance of the sender at const eval time to evaluate this function. The template parameter can be enriched with CD and ref qualification to communicate to us exactly how we will be qualified when we are connected. Which brings us to that last thing on the slide, the basis operation of a sender whereby it is connected to a receiver. Because a synchronous function on its own is useless. It doesn't do anything. Synchronous functions don't invoke themselves. They are invoked by callers from a certain location by which a return channel is established. And we need exactly the same thing in the asynchronous domain. We need to provide an asynchronous operation with a channel by which it can actually send completion signatures. We need to give it a receiver. This raises the question of what exactly a receiver is, and so we turn to looking at its interface in turn. Of course, we have a nested type alias which opts us into the std execution receiver concept, And then we have member functions for each of the possible completion signatures we can receive. We could receive completion on the set value, set error, or set stop completion signal, and so we have corresponding member functions which are appropriately parameterized based on the set of completion signatures we wish to receive. But connect doesn't return void. It doesn't spawn asynchronous execution in the background. It returns an operation state, and in so doing models the two remaining pieces of our synchronous function call protocol. Synchronous functions receive a stack frame they can use for variables with automatic storage duration, and that is what this operation state is analogous to. But looking at it, it's not just an opaque type that has the variables that morally have automatic storage duration. It also has the basis operation start. Because when you call a synchronous function, you do two things, not one, which are separated in the stood execution ecosystem. You both provide a return channel for that function you're calling, and then you jump into it and give it permission to use the CPU to make forward progress. The analog of this jump into the body of the function is exactly what we get from start on an operation state. When you form an operation state by calling connect, it represents latent execution. Only once start is called is it given permission to make forward progress. And we can take these relationships and render them graphically. A sender rendered as a fully curried version of a function, a receiver as its return channel. They must, of course, be brought together via connect, yielding an operation state, which we can then give permission to actually make asynchronous forward progress by calling start. Now that we've completed this overview of stood execution, we can actually take a look at when all and how it behaves so we can extend it. The first thing to understand about when all is it has a limitation that it only admits senders with, at most, one value completion signature. That power to replace extrinsic sum types need not apply when passing a sender to when all. It will be rejected. Thereafter, the behavior of when all is best understood in terms of how it behaves when its child operations complete. If a child completes reporting success by sending value, we simply store the value sent thereby in the operation state. We can't necessarily do anything with them now because subsequent children may need to complete before finalization. If, on the other hand, a child reports error or stopped, we now know that we can't wait for all of the children to complete successfully because at least one of them has neglected to do so. This renders the execution of the remaining children defunct and unnecessary, and so we request they send set stopped as soon as possible and not waste time and resources. Of course, we store the first error or stop completion signature that we receive from a child so that we can send it later when we finalize. When we finalize, when the last child arrives, we look at the manner in which all of our children arrived. If they all completed successfully, we concatenate the values sent thereby together and send them on our value channel in turn. Otherwise, we simply send the error or stop completion we receive first downstream to our receiver. With this understood, we can now understand how when all range is going to extend this formulation. The most significant extension it provides is the fact that the cardinality of the children is no longer fixed. We can't use this trick of taking all the values sent by the children and concatenating them together because we don't know their cardinality. We couldn't possibly advertise such a completion signature, and so we're going to need to get a container involved. We're going to pick vector. The problem with this choice, however, is that our children could neglect to send any values whatsoever. And so we will special case this case and say that we'll just send no values in turn. After all, 0 times n is still 0, and so there's no loss of information here. On the flip side of this edge case, our children could be taking advantage of the power stood execution has to eliminate the need for extrinsic product types. Maybe they sent multiple values, and so in this case, we're going to send a stood vector of a tuple of those values. And we can immediately render this transformation in code. We can simply write a trait which computes the appropriate vector. The primary class template simply synthesizes a vector of tuples of decaying all the arguments. The reason we decay all the arguments is because decay is the transformation which obtains the storage type for a t, and we're trying to actually store a t. We have a specialized version which picks out that special case of exactly one value and just renders it as a vector without a layer of tuple wrapping. We have a type alias, so we don't have the type in everywhere, and the problem is solved. But we're trying to write a generic algorithm. We're trying to give our users maximal reusability. And vector has 2 template parameters, not just one. It doesn't just admit an element type, it also admits an allocator. And so if we're to be truly flexible and generic, we should give our downstream consumers the ability to parameterize that second template parameter as well. But what's the idiomatic way to obtain such customization in the stood execution environment? The answer to that is that we don't yet understand that ecosystem well enough to answer the question. We understand we have senders and receivers and that together they form an operation state. But what we haven't yet revealed is that receivers have an associated environment, a collection of queries for associated objects, and one of those associated objects is an allocator. Now that we understand the allocator comes from the receiver's environment, we can write some helpers that assist us in this task. A constrained version of the function which returns the associated allocator if the environment has one, and if the environment doesn't have one, we simply return std vector. We do exactly what it was vector would have done if we'd only provided it one explicit template argument. Then we have a helper type alias, and we simply turn around and stamp out 2 additional helpers to respect the fact that standard library containers really like it when you give them appropriately rebound allocators. Now we can revisit our trait and enrich it with this allocator awareness. We have a vector type alias which synthesizes an appropriate vector from a T and an environment, and then we simply enrich our trait with a leading environment and switch them over to use our new type alias. Now we've allowed our vector to be enriched by our user's customization. But this is just pondering the value completions. It's just pondering the occasion where our children send a value. It doesn't deal with the fact that we may not send a vector at all. It doesn't deal with the fact that children might send errors or stopped. For that, we're going to need to actually do some template metaprogramming, which leaves us considering the techniques that we could use to accomplish this. We could use regular template metaprogramming, but it's verbose and time-consuming, and this is not a template metaprogramming talk. We could simplify this by using Boost MP11, but this is also not a Boost MP11 talk. Almost as though they knew this was coming, the authors of P2300 proposed std execution transform completion signatures, which does exactly what we want. But then in P3557, Library Evolution Working Group removed transform completion signatures, and so we can't use it anymore. Of course, P3557 contemplates replacement techniques for achieving these transformations, but it proposes none of them, which leaves us at an impasse. Until we remember this is a talk about std execution. Std execution is a C++26 feature. This is a C++26 talk, which means I can use C++26 features to do the template metaprogramming I want to do. I can simply use reflection to implement this in const eval functions. To start with, we're going to define a reflection space helper that allows me to synthesize completion signature types. Recall, each completion signature is a function type with the channel it's sent on as the return type and the values transmitted thereby as the parameters there too. And so we have a type alias helper that simply stamps out the function type. Then we have a const eval reflection-based function that takes in a reflection of the tag type and a range of reflections of all of the parameters. It rectifies these into a single list, it substitutes them into our type alias, it strips the alias layer off with the alias, and it returns a reflection of the new completion signature type. But this just forms one completion signature. We want to transform all of them, and so that's what we're going to do in our completion signatures function. We are parameterized by a reflection of the completion signatures of our child. We are also parameterized by a reflection of our environment type, since we need that to obtain the allocator type. But we're not going to just synthesize the set of completion signatures we're going to yield. We are also going to seamlessly validate the input completion signatures. We're going to reject input completion signatures which cannot have when all range implemented on top of them, and that is the reason for that Boolean at the top of the function. We need to record whether or not we've already found a value completion because recall from earlier, subsequent value completions render when all range unimplementable. Then we simply prepare a vector to hold our result completion signatures, and we have a helper lambda which respects the fact that a valid instantiation of std execution completion signatures cannot contain duplicates. And so when we would emit a completion signature, we check to see if it's already in the vector, and if it is, we neglect to add it. Otherwise, we push it in at the back. Armed with this, we recognize the fact that std execution completion signatures transmits the completion signatures based on its template arguments. And so we use template arguments to extract those, and then we simply loop over them with a simple range-based for loop. We go to each one and we ask it what the return type of the function type it represents is, because this is how completion signatures are transmitted. Then we simply check to see if this is a set stop completion signature, and if it is, we simply copy it over. Set stop is always nullary, so we don't need to do any processing or consideration of its arguments. In the case of set error or set value, however, there may be arguments that we need to consider. We need to extract those by using parameters of on the signature, and then we need to loop over each and every one of them. Recall that we may need to store them somewhere, so we're going to need to decay them. But there's also edge cases wherein when all range is not implementable. Imagine we have an operation that sends things that cannot be decay copied. We can't store them in our operation state for later, and so when all range is unimplementable. But then as we finalize, we want to move those out of storage, and so if we can't do that, when all range is also unimplementable. And so we check both of these properties of each and every argument. If we find that we can't decay, copy, and move those arguments, we throw an exception. Reaching such a throw statement causes this to fail to be a constant expression and bails out and says that we can't actually implement when all range. Otherwise, there's another edge case. Storing and retrieving these values might possibly throw an exception. You might think we'll just let that bubble up the stack, but that would be reporting an exception in a synchronous way. We wouldn't be completing the asynchronous operation whose context we're in. We would be throwing an exception to some random part of the program that's not equipped to handle or contextualize it. And so we must identify the situation, and we must enrich our set of completion signatures with a throwing completion signature to indicate to our downstream receiver that this operation in this circumstance might possibly throw an exception. With all of this done, we can simply replace that argument with its decayed version, since that we will send downstream to our consumers, and then we can move on and simply handle set error of t. If we see a set error t completion signature, we just stamp out a new set error t completion signature with the decayed types rather than the original types, and we're done. Which leaves value completion signatures, which have to be checked to make sure we don't get multiple of them. If we find that this is a duplicate, we've already received a set value completion signature, we throw an expression and we fail to be a constant expression. Otherwise, we need to go and check to see if it has no arguments. If it has no arguments, we simply emit set value of t of no arguments. Otherwise, we need to instantiate our 2-vector t type alias. We recall that it has a leading environment parameter, and so we splice the reflection of the environment in at the beginning of our vector. And then we substitute those arguments into 2-vector of t, but that just obtains the reflection of a type alias. And so we extract the type it refers to via d-alias, we pass it into make completion signature, and we add that overall completion signature to our output set. As we fall off the end of the range-based for loop, we simply substitute into stood execution completion signatures, and we've obtained our final completion signatures instantiation. And I didn't just write this code by looking at the body of P2996. I actually implemented this using a reflection supporting Clang fork that Dan Katz implemented. This passes all of my unit tests. You can actually use this whenever it is your compiler actually supports it. But this is just us reporting how we would complete if we were ever actually implemented. To think about how we're actually going to be implemented, we need to look at the locus of asynchronous execution, the operation state. And surely, since this is a C++ type, it's going to have some members, it's going to have some subcomponents that we're going to implement. And so we can split it into its constituent parts. But if we're going to have children, we're probably going to have a collection of those, and each of those is going to contain components that we're going to have to implement. What we've done here is we prepared a map through the implementation of when all range. We can simply visit each of these boxes, implement them, and then take a step back and implement the overall operation state and the overall child state, which begins our traversal thereof. Let's think about how we're going to store the receiver. This might seem like a very easy question to answer. A receiver is a C++ object, and an operation state is a C++ object. So surely the receiver can just be a member of the operation state, right? Well, let's think about how asynchronous operation actually occurs in the real world. When we're in the synchronous domain, we have functions calling other functions, and so their stack frames are located in a hierarchy. And in asynchronous execution, the same thing is probably the case. Our operation state probably isn't some complete object. It's probably being used as an implementation detail of some parent operation. And so we're nested inside of the parent operation state. But we know that the receiver represents the return channel for our asynchronous operation. It was provided by that parent and contains and encapsulates the parent's continuation logic for us. And so in order to implement that receiver, the parent probably wrote it in such a way that it just contains a pointer back to the parent operation state so they can access all the members thereof. But then we realize that the offset of the child operation state is statically known from the type of the parent. We should, in principle, be able to go from the child to the parent without actually storing 8 bytes worth of pointer. And this may seem like a very small issue until you remember that this cost of 8 bytes manifests itself at every single level of composition. If you take some asynchronous operation and realize it's actually 2 reusable parts and shatter them, the cost is 8 bytes. You've belied that fundamental C++ principle of zero cost abstractions. And so Lewis Baker and Brian St. Amour prepared this paper, which proposes the concept of an inlineable receiver. which subsumes receiver and additionally adds the protocol that a PR value receiver can be synthesized from a pointer to a child operation state. Inside of this function, the parent operation pointer is synthesized from the child operation pointer, and a receiver is synthesized out of thin air. We elide the need to incur the cost of those 8 bytes. But this raises a problem. Now we have a compile time fork in how we store the receiver. It's not as simple as having a member of receiver type. And P3425 discusses but does not propose a solution to this problem, the inlineable operation state CRTP base class. Here we see the primary class template, which is not that interesting. It actually stores the receiver, since the receiver is not inlineable in this case, has a constructor which populates it, and has getReceiver, which returns a mutable L value reference thereto. Where things get interesting is in the specialization, which is constrained on inlineable receiver. Notice we have no data member, we're not incurring that cost of 8 bytes. Our constructor simply discards its argument. GetReceiver no longer returns a mutable L value reference, it returns a PR value, which is synthesized on the fly. We take a pointer to ourselves and we use CRTP to downcast it to a pointer to derived, and we provide that to make receiver 4 to allow the parent operation to synthesize the receiver for us out of thin air. With that problem solved for now, we can move on to the next part of our map through this problem domain, which is implementing the stop source. But that brings us to something uncomfortable. Throughout this talk, I've simply asserted that we can make child operations stop somehow, that they could send set stop for some reason. We haven't actually discussed why that might occur. And the reason for that is another part of the stood execution ecosystem we haven't yet discussed. We understand receivers have associated environments, and that those environments can be interrogated as to their associated allocator. But what we haven't yet reviewed is that environments can also be interrogated as to their stop token, some channel through which stop requests can flow. Since our operation is parameterized by the receiver, which yields the environment, which yields the stop token, our operation is transitively parameterized by the stop token. We can receive those stop requests and handle them appropriately. But the fact that stop requests exist and are emitted is insufficient. Where do they come from? They come from a stop source which yields the stop token. But notably, you can't interrogate the stop token as to its source. You can't use a stop token to actually request stop. Let's contextualize this to WhenAllRange. WhenAllRange's operation state was formed from a sender and a receiver, and so of course it has access to some environment which can yield a stop token which is from some stop source. If we're simply being naive, the way we parameterize our children might simply be to pass through the only environment we have access to, and that is the environment associated with our receiver. And this has some elegance to it. Our downstream consumer can request stop against their stop source. The stop token will report it through to our children. Our children will stop and will invoke our finalization logic, and we will stop in turn. But in the case where our children send set error, we want the ability to request that all of our children stop. We want to actually emit new stop requests ourselves. And we can't do this in this formulation because we don't have access to the stop source, which motivates that entry on our map through this talk, which motivates the fact that the operation state of WhenAllRange owns its own stop source to which it can submit stop requests and from which it can obtain the stop token. Given the appropriate environment type, it can parameterize its children on these stop tokens, and now we can actually request that our children stop whenever we want them to. But we've lost something in this transformation. The stop token we receive from downstream is no longer connected through to our children. If our downstream consumer asks that we stop, we will ignore them. We will only stop our children if we have reason to do so because of the way another of our children completed. And so what we need is an association between our downstream stop token and our own stop source. We need a stop callback, which is invoked whenever a stop request is submitted through our downstream stop token and which re-emits it into our stop source. And we're going to begin our journey through implementing this entire diagram with exactly that stop callback, with a simple invocable type which has a reference to our stop source and which, upon invocation, simply requests stop there against. Assuming we actually set up some way for the stop token to invoke this invocable, we will have implicitly formed our association. Which brings us to the next level of analysis, actually implementing the combination of our stop source and our stop callback, taking and deriving from stood in place stop source to get access to all of its functionality, but implement chain stop source which extends it parameterized on the type of our downstream stop token. Notice that we go to that token and we ask it what the type of a callback is that would associate that token with the invocable that we just authored. And then we have a member of that type which we initialize in our constructor. As soon as this stop source is constructed, it will automatically re-emit stop requests from downstream into our stop source, giving us the flexibility to not only request our children stop ourselves, but also to have them stop whenever they requested to by our consumer. Or at least that would be the case if we'd written that environment type, which is exactly what we're going to do now. But as we think about it, we don't just want to give our children a stop token because there may be an infinite number of other parameterizations flowing through from our consumer. We saw one earlier in the talk, an allocator. Surely we want our children to be transitively parameterized thereby as well. And so our stop source environment doesn't just wrap a reference to a stop source from which it can then stop tokens, but it also wraps that nested environment to pass through all the other queries too. We have a unary invocable query member function which receives the get stop token query and goes to our stop source and returns our particular stop token, thereby overriding that query for our nested environment. But for every other query supported by that nested environment, we simply pass it through. We allow this parameterization to transitively affect our children as well as us. Which brings us to the next entry on our map through this talk. We need some way to store an error or stop completion signal if one arrives from our children. But this idea that we would store an error or a stopped completion signature falls short of how generic it can actually be. Why would we store just stopped and error completion signatures? Why don't we write a generic type that can store any kind of completion signature, which we can then reuse in the children? And so we need to come up with a generic interface for doing exactly this. We need to eventually back up this interface with some code. We have the ability to arrive with some completion signature, which is discriminated by some tag. We actually pass that tag type in as a value which will prove important later on in the talk. But just storing the completion signature doesn't get us anything. We need some way to also extract that completion signature to visit it out into a visitor. But there's no point in doing that if we can't actually understand whether or not a completion signature is contained by this object. After all, we may be trying to visit the main operation state storage for error and stop completions, but all of the children completed successfully. And so visit returns a Boolean which indicates to us whether or not there was actually a completion signature herein, which we can examine to determine whether or not we need to go off and inspect the storage for another type of completion signature. And we can write code that actually models this. We have an incomplete primary class template because specialization is going to do the lifting for us. The specialization for no completion signatures at all is completely vacuous. We don't have the ability to arrive because there are no completion signatures, and so we should statically know we never arrive here at. The visit function is vacuously implemented to always return false. At first, this may seem unnecessary, but consider the case where you have a range of children that always complete successfully. Then the kind of completion signature you want to store in the main operation state is the empty set. There are no error or stop completion signatures, and so the specialization is important. But the thing we really care about is actually storing completion signatures, and so let's prepare a type trait that allows us to determine the storage type of a completion signature. We use specialization to extract the tag and arguments, and then we stamp it out into a tuple which decays all of the arguments, once again because we're storing them. Which brings us to the specialization that actually does work, that actually activates when we have completion signatures to store. We go and we transform all of the signatures into a tuple that stores them, and then we uniqueify that list with MP11 unique. And this is because when you decay tref and tref, you get t in both cases, and we don't want to deal with the vagaries of interacting with a variant with duplicate alternatives. Note that we have monostate as a leading alternative because when default constructed, we will be having no signatures stored herein. Which brings us to the code that actually executes when we arrive, when we want to actually store a completion signature represented by some arguments. But note that we carefully craft this no-except expression. We carefully craft this no-except expression because throughout the remainder of the talk, looking at whether or not expressions throw is going to be vitally important. Recall that when synthesizing our completion signatures, we only conditionally reported that we could asynchronously throw an exception. And therefore determining whether or not some expression can throw or not, and storing a throwing completion signature only if it actually fails will become vitally important. And so we report that this doesn't throw an exception if we can no-throw construct the storage type of this signature from the arguments representing that signature. Then we actually go to our variant and we emplace the appropriate type. But as I just discussed, in certain instances, this might throw an exception. We catch the exception, but in this edge case, the variant is now in that dreaded state. It is now valueless by exception. And we don't want to deal with that. And so we simply assign monostate back to it and then re-emit the exception out through the function call boundary. But storing is nothing without visiting, and if we're going to pay special care and attention to no except here, surely we're going to do it everywhere. And so we prepare a variable template which extracts the tag and arguments through specialization and determines whether or not visiting a certain signature into a certain visitor throws an exception. Armed with this, we can now implement visit. We have the appropriate no except clause which we form via a fold expression over the variable template that we just wrote. Then we simply visit into an overload and we extract all of the tuples and apply them into our visitor and return true, whereas monostate we special case and return false. In this case, nothing must have been stored in this storage. But now we have to consider something. We've written the class that we're going to use to store the value completion signatures flowing from our children, but we're not sending those values downstream as separate storage for completion signatures in the child states. We're going to gather them into a vector. And if you thought about interacting with a vector at any level of seriousness, you know that putting elements into it can possibly throw exceptions. And if we're going to do this as the last step of our asynchronous execution, don't we always possibly throw exceptions? Why do we bother paying all that special care and attention to no except? And the answer to this is because vector only throws due to reallocation if it reallocates. You know exactly when it will reallocate. It will reallocate if an assertion would cause the size to exceed the capacity. And so maybe we can just take and we can store result storage on our main operation state. We can pre-allocate a vector when we're constructed and ensure that we never allocate at finalization. And this might seem like I'm cheating a little bit, like I'm doing some sleight of hand just to justify calculating complicated no except clauses. But this is an approach that's actually supported by the authors of P2300. The idea that at connect time when an operation state is constructed, you should go off and acquire all of the resources that execution will require. Thereafter, you can reduce the number of instances wherein your asynchronous execution will fail. And so, resting easy knowing that this is supported by the authors of P2300, we can draft up another generic interface. Because after all, we're not always going to have a vector. It may be the case that our children all send nothing. And so we need an interface to result storage we can use generically. It has a binary constructor which takes the number of children, and of course the allocator it's going to use to obtain the storage. Then we have reset, which allows us to forcibly discard all of the memory we've allocated. And this is because, unfortunately, we don't always complete in success. We don't always actually need this vector. And when we don't need the vector, it would be really nice if we went and handed that allocation back to the allocator the user provided us before we told them we're done. It would be nice if we released our hold on these resources, and that is what reset does. We have a function call operator, which, if you contextualize this vis-a-vis the class template we just wrote, integrates beautifully with visit. We can just pass one of these result storages into visit, and we'll transparently propagate the completion signature stored thereby into this. And so this is what this does. We invoke it for each child as we're gathering all of the results. Then finally, at the end, we pass the receiver into complete, and whatever is stored inside here gets sent through to the receiver on the value channel. Maybe this will make a bit more sense if we look at how it's implemented. We accept a template parameter that gives us only the value completion signatures because after all, we're unconcerned with the error and stop completion signatures. Those are stored somewhere else. We also, of course, have the environment since we need somewhere to get an allocator from. Then we turn to a specialization which has no completion signatures at all. And this may seem interesting if you're used to the synchronous domain. The idea you may have some analog of a function which never completes successfully. This is somehow even stronger than the idea of no return. But these asynchronous operations are wildly useful. I authored one in my talk in Tel Aviv last year. Imagine you have a sender that represents the asynchronous execution of an entire network server, which is exactly what I wrote in that talk. Does that network server ever complete successfully? But what that mean? It only reports errors and stop, and so it's possible that the asynchronous operations we're composing have no value completion signatures. In that case, we simply have a vacuous specialization of result. The constructor does nothing, reset does nothing, it has no function call operator, and completing in this way is, of course, unreachable. Which brings us to storage for the case when we actually have a value completion signature, but it doesn't accept any arguments. We don't need a vector, we don't need to allocate. And so we once again have a vacuous constructor, a vacuous reset operation, but this time we at least have a function call operator, even if it's vacuous. But then complete actually needs to do something. We're actually going to, hopefully, complete this overall asynchronous operation, and so provided with the receiver, we call set value thereupon. but we provide no additional arguments because, of course, we are mirroring through a set value completion signature with no arguments. Which brings us to the meaningful specialization, the one where we actually have a set value completion signature with many arguments. As I go through this, remember, I don't need to deal with the case where I have multiple completion signatures because we banned that outright as a port over from when all. We know there will only ever be, at most, one value completion signature. And so we go and we obtain the storage type for it from our 2-vector t type alias. We extract the element type therefrom, and we have an optional storage type. The reason the storage type is optional is because destroying a vector is the only way to make absolutely certain that it's not holding on to any memory. Destroy the allocator and ensure that your shrink to fit call wasn't completely ignored as the implementation is allowed to do. Then we have a constructor which actually does something. It actually constructs that vector from the associated allocator with our environment. And then we go off to it at construct time and we reserve the appropriate amount of storage. We ensure that we will never throw allocation-related exceptions for the remainder of the operation here at connect time. Reset, of course, simply disengages that optional. And then when we arrive with a completion signature, when we're trying to gather it from the child operation state, note that our no except clause is carefully chosen and ignores the fact that we could throw an exception for allocation. Because, of course, we can't. We simply go and we emplace back, knowing that there is enough storage to emplace that value because we allocated enough space for all of the children to arrive. Ruslan.
So, and if the constructor of the argument itself throws, or did we eliminate that as well?
Right, that's why we have is no throw constructible of the element from the arguments. Now, moving on, we can finally implement complete. Given a receiver, we simply complete with set value, but this time we actually send our vector by moving it. Which finally lets us zoom out and look at the operation state. We can finally dive in to that implementation. But in so doing, we have to address something that's remained latent up until this point. We've written generic storage for completion signatures, and we intend to store different completion signatures in different places. We've written storage for the result, which synthesizes that storage from the type of only the value completion signatures. And both of these imply that we have some way to take a set of completion signatures and shatter it into two sets of completion signatures based on some predicate. But we haven't seen a utility to do that so far, and so we need to dive back into reflection. We need to write filter completion signatures. Given the reflection of an instantiation of stood execution completion signatures and a predicate, we simply use simple range logic to filter according to the predicate. We take the signatures that match and we substitute them back into stood execution completion signatures, and we return a reflection thereof. We can then turn around and use this to implement two template type aliases. At first, the code on this slide may look overwhelming, so let's walk through it carefully. We have value completion signatures, and from the name, we suppose that it's supposed to resolve to only the value completion signatures of its template argument. With that in mind, let's try and read the expression it's equal to from the inside out. We have a predicate which admits only value completion signatures, exactly what we expect. And then above that, we have a reflection of the signatures, which of course we need because we need to call filter completion signatures. Then at constant evaluation time, we call filter completion signatures, and it returns us a reflection of the type that we want. Then we use the reflection splice operator to simply reify this type and cause the template type alias instantiation to resolve thereto. This implements exactly what we want. Other completion signatures is exactly the same, except the predicate we provide is exactly the opposite predicate. Instead of selecting only the value completion signatures, we select only set error and set stopped. Which leaves us with one last thing we want to do. We want to extract the sender type from our range. And we're going to do that by simply decaying the range reference type. Now we can finally actually look at the implementation of the operation state. We can actually open that class and start looking through its nested type computations, but first, we see that it derives from inlineable operation state. That first entry on our map through the talk is actually being used. We can check that off. We've solved the problem of storing the receiver. We give that base class a different name because I didn't really feel like typing out inlineable operation state of operation state, comma, receiver everywhere on these slides. And then we have simple type aliases that resolve to our sender type, the receiver's environment, and of course, that environment type that we're going to parameterize our children on, which provides those stop tokens we want to provide. Then we go to our child operations sender and we get its completion signatures. We get the ways in which it completes because we're going to use this throughout the remainder of this operation state. We immediately use it, in fact, to obtain our result type by instantiating result on that and the receiver's environment from which it will extract an allocator, thereby giving us the result storage we need to actually complete the operation. We forward declare a state for the child. We're going to look at that later. And then we have a list of those states, which of course uses the appropriate allocator. Turning to the member variables of this class, we get to check off another of those things we saw on the map. We have a chain stop source member with an appropriate template parameter. And so we can simply check that off. We implemented it as a reusable component, and now we actually have it as an instance. Then we have 2 atomics, which allow us to do bookkeeping about the arrival of our children. We count the number that have actually arrived so we know when it's time to finalize, and we have a bool that tracks whether or not we've stored an error or stopped completion signature, because recall, we only want to do that for the first one. Then we actually get to checking off the storage for pending, stopped, and error completion signatures, but this is quite a bit of code. It's difficult to understand, so we're going to walk through this from the inside out. We obtain a reflection of our child's completion signatures. But that's actually a lie. We're retaining a reflection of a type alias that resolves to our child completion signatures, and so we strip off the alias layer to get a reflection of the type we actually want. We do exactly the same thing to obtain the environment in which our children will be connected, and then we pass those 2 parameters into completion signatures. It runs at constant evaluation time, and it returns to us a reflection of the completion signatures that we are going to yield when we complete. We immediately take that reflection and we splice it in, and then we pass that set of completion signatures to other completion signatures, which simply throws away the value completion signatures and gives us only the error or stop completion signatures. Then we pass just this subset of the completion signatures into storage for completion signatures, and now we have storage for only the error and stopped completion signatures. Exactly what we wanted to check off that box. We have an optional list of our child states, unoptional so we can, of course, completely destroy it and deallocate all memory before we complete this operation. And then we end things out by checking off that last box, storage for the result, something to hold on to that pre-allocated vector. Speaking of storage for that pre-allocated vector, we could just write a helper function that actually completes this operation in success. We go and we destroy all the children, and then we go to the central storage for our populated vector, and we ask it to complete our receiver. We've abstracted this away sufficiently that we can complete the operation in only 2 lines of code. Which brings us to the public-facing interface, the constructor which will be called at connect time, which is something we can deduce from its parameterization. It receives the range from the receiver, from the sender, and of course just receives the receiver. We take the receiver and we simply punt it through to the base class, which will figure out whether it needs to store it or discard it because it's inlineable. And then we form that association between the stop token provided by our consumer and our stop source by constructing it with a stop token sourced from the environment from our receiver. Now we can actually create all the child states. We create an appropriate list associated with an appropriate allocator, and we loop over all the senders in our range. For each of them, we construct a child state. We haven't seen this constructor yet, but rest assured it will actually accept a reference back to this parent operation state and a sender that it's actually going to manage. Once we've synthesized this list, we simply return it and populate states underscore, which was very important to do early because we need access to states underscore in order to decide exactly how much memory to allocate. You might say to yourself, why didn't he just get the size of the range? And that's because some ranges aren't sized. We need to actually iterate it into our list in order to be able to reliably figure out how big it is. Of course, we do pass through that allocator to make sure that however our user wants allocations handled are how they're actually handled. Which brings us to the basis operation of an operation state, the ability to start it and actually spawn that latent asynchronous execution. Matt?
Why is it a list and not a vector of the states?
So I have a lightning talk about that.
Cool.
And the answer to that is operation states are immovable. So you can only put them in a vector if you use the from range constructor and it's a size range.
Okay.
Otherwise, you need to use list because otherwise you have no idea how much storage, and vector might try to move things, and operation states are immovable. The only reason they can even be returned from connect is because of C++17 guaranteed RVO.
So why aren't you using deck then?
I try to not use deck. That's the closest I can give you to an actual answer is I just didn't want to use deck.
List work.
Yeah. So this function actually starts the operation. We do have an edge case because ranges can be empty. And if we have no children, we have no asynchronous computation to kick off. And so we're complete immediately. And so we simply complete synchronously in line. This is something that std execution actually allows. And so this is completely acceptable. If we have children, we of course need to traverse across them and ask the asynchronous execution inside of each one to start. But notice that when I do this, I don't pay any attention to exceptions. There's no exception safety. There's no attempt to unwind the states I've already started if an exception is transmitted. And that's because starting an operation state simply cannot throw exceptions. Starting is mandated to be no except because when you start, you transition to asynchronous execution. If an error occurs, it must be caught and sent through to the receiver in the same way that you wouldn't consider returning from a synchronous function by simply doing something random somewhere else in the program. But there's actually a very subtle problem with the code on the slide. And that subtle problem falls out of the fact that I mentioned that asynchronous operations in std execution can complete synchronously in line with start. If that's possible for us, then it must equally be possible for all of our children. And so it might be the case that every time I call start, the child completes synchronously. This is fine for the first few children, but what about for the last child? I call start and the last child completes synchronously in line. It's going to, of course, send a completion signal to a receiver that implements part of when all range's logic, which we'll see in just a few moments later in the talk. That logic is going to finalize when all range and is going to send a completion signal to our receiver in turn. Imagine what this would mean in the synchronous world. We've now returned from our synchronous function. The stack frame for that function is gone. But this operation state is the analog of a synchronous stack frame. That receiver is well within its rights to simply end the lifetime of the operation state. And then when we return all the way up to this function, star this is outside of its lifetime. That's, of course, completely acceptable. That has well-defined behavior. But then we reach the bottom of the range-based for loop. We go up to the top of the range-based for loop into the compiler-generated code therein. We increment the iterator. An iterator which refers to a collection which is a member of star this, which is outside of its lifetime, which is undefined behavior. We compare that against the end iterator of the same collection, which is also undefined behavior. I actually have a test suite in my test for when all range that segmentation faults if you use this implementation. And so we need to manually deal with the iterators ourselves. We need to throw away that nice neat implementation and grab ourselves an iterator and see if it's already at end. If it is, we complete synchronously inline. Otherwise, we do manual bookkeeping as we traverse that range. We grab a reference to the current state, and then we bump the iterator. We check to see if this is the last state, and we store that information on the stack, and then we start the asynchronous computation of the child. If it completes synchronously inline and causes the lifetime of star this to end, it doesn't matter. As we return all the way to this code, we will look at a stack variable, not a member of star this. We'll then break and return from the function without ever examining a member of ourselves. But of course, everything that we've done doesn't accomplish anything if our operation state doesn't say that it's an operation state. And so we need to have the appropriate nested type alias to advertise that fact. Which means we should now turn our attention to looking at our child states. But as we look at this, given the information we've already been exposed to, we can imagine these child states are probably more complicated than this. We've in fact seen that the construction of a child state is parameterized by a reference back to our main operation state, and we don't see that in our diagram. And then we know from the formulation of operation states that we probably inject a receiver into that operation state when we form it, and so we should probably see that on the diagram. Instead of this simple diagram, it should probably look something like this. But as we stare at this diagram, and we stare at that receiver, and we reconcile it with everything we know that receiver implements logic from when all range. We know we provided that receiver. We know when completion signals are sent to that receiver, we're going to want to take the value completion signatures and store them in the pending value in the child state. On the other hand, if it's an error or stop completion signal, we want to chase that parent reference back to the main operation state. And that means that receiver is probably just a pointer back to the child state, which means we're on the other side of the protocol from P3425. We don't want to just store inlineable receivers. We want to actually write one. And P3425 considers but does not propose a utility to do exactly this. Another CRTP-based class called child operation state. Unsurprisingly, it contains an implementation detail receiver, which is an inlineable receiver. It simply contains a pointer back to the parent op. It opts into being a receiver through a nested type alias. It has a constructor from just the parent op pointer, and it has make receiver for. But we would expect inside of make receiver for to see a bunch of gnarly casts by which we synthesize the pointer of the parent operation from the child. And instead, we just have a comment that asks you to use your imagination. And P3425 doesn't do this. P3425 goes to a lot of words to try to explain how this protocol might be implementable. But then under review, someone said that they don't think that's actually well-defined in general, and maybe if you add some calls to launder, it will be more well-defined. But launder doesn't actually increase the set of bytes which are reachable through a pointer, and it's unlikely that the bytes of the parent operation state are reachable through pointers to the child. And then someone said that there's a paper in flight that actually brings the object model of C++ more in line with C, and this will become well-defined behavior. And this is not a talk about any of that, actually. And so maybe I'll just leave all of that undefined behavior code off the slides. And if you feel like implementing it, you can actually type offset of yourself. For the time being, I'm going to write code that I'm reasonably sure has well-defined behavior. And so we simply see all of the basis operations of a receiver forwarded through to the parent. This was implicit in our formulation of an inlineable receiver. It's just a transparent wrapper around the parent. Looking at the tail of the class, we see how it's initialized, but this is very disinteresting because most of it is left to your imagination. What we can glean from this is that constructing this base class actually connects our sender with the receiver, and then we can actually call start on it to start the latent execution. Of course, we have no idea how that connect call occurs or where that operation state is stored. We simply leave that up to our imagination and trust that someone somewhere wrote offset of at least one time. Which brings us to the tail end of our operation state where we simply perform some type computations necessary to implement the child. We have a canned version of child operation state with the needful parameters, and then we have this curious state-based class. It simply holds a reference back to the main operation state and constructs by binding that reference. And for now, the need for this is not clear. It will become clear later, but suffice it to say it is the first base class of our child state, not any other base. The second base is that child operation state CRT base class, and then we see that our only member is storage for the value completion signatures. Moving on, we get to perhaps the most important function in the entire talk, maybe complete, which possibly finalizes the operation if it is acceptable to do so. But in this preamble, we just have some convenience. We rename that self underscore reference back to the operation state to op, and we have an error lambda which attempts to visit the error or stop storage in the main operation state, and if it succeeds in visiting it, we'll perform the necessary cleanup by deallocating all of the children and throwing away that allocated vector, and then using a neat template metaprogramming technique to dispatch the appropriate completion signal. Because of the fact that our storage for completion signature stores the tag, because we're parameterizing the tag, we don't need to figure out whether this is a stopped or error completion signature. We can simply invoke the tag and it will implement that logic for us. But this innocent-looking preamble is more than just an innocent-looking preamble. There's something very important lurking inside these two lines of code. That binding of a local reference is not just me giving a convenient name to op, it's actually a critical tool for correctness. Consider what happens in the second outlined line of code. We destroy all the child states. But star this is a child state. As soon as we return from this call, star this is outside of its lifetime. Self underscore is a member of star this. If we consulted with self underscore by on the next line, writing self underscore result underscore, that would be undefined behavior. And so taking that reference and putting it on the stack is vital for correctness. But we can't even proceed with finalization if we don't know it's time to finalize. And so we do this with a single atomic increment with acquired release semantics. This is the only place in this entire presentation where I actually establish an interthread happens before relationship. If we're not the last child in, we simply return. Otherwise, we go to the central operation state and we ask if any of our children completed with error or stopped. If they did, the error lambda will handle the finalization of this operation and we are serendipitously done. Otherwise, we actually need to walk through all of the children and gather all of the ways in which they completed successfully. And so we traverse all of the child states. But then we do some magic involving no throw. And it is here that we actually benefit from all those careful no except clauses we wrote earlier. We interrogate the action of propagating a stored value completion signature through to the final result to see whether or not it will throw. This no except evaluates to the correct result because of all of the no except clauses we wrote throughout the beginning of the talk. Then we have an impl lambda which actually propagates that value from the storage to the final result, and which has the appropriate no except clause. We also report that we know that a value is stored in every state because earlier we established none of them ended in error. Matt.
So you are having the children store the values so that when you move them into the vector at the end, you have a guaranteed ordering to the vector?
Yes. Okay. Yeah, I have another implementation of when all range that does this by keeping two parallel vectors, one with the results and one with the index of that child, and then sorts the first one based on the second one. And I actually had a conversation last night where I was bemoaning to somebody that, David's in the room, that vector is insufficiently safe. And I really wish that I could break its invariance and place the objects into it and manually clean them up at the end, because then I'd have to move them never. But unfortunately, vector is really safe, and I didn't feel like putting cast down to private bases and breaking its invariance on the slide. So this technique is just the best one that we have. Is that sufficiently horrifying for you, David?
Sounds like it.
Okay. Now that we've defined both of these, we can move on to actually using them through a curious if context for cascade. And the reason we need this if context for cascade is because of the synthesis of completion signatures we saw earlier in the talk. Remember, we inspected each and every value might have to store and retrieve, and we asked whether or not that operation can throw. If none of those operations throw, we may not have advertised a throwing completion signature. If we didn't advertise a throwing completion signature, simply trying to compile that catch block would fail the compilation. And so we can't emit that catch block in the case when we don't store a throwing completion signature, and so we need this if context for branch. If we don't throw an exception, we simply perform the operation without a try catch. But if we do throw, we know through our analysis that we recorded a throwing completion signature at the beginning, and so we emit a try catch. And when we catch the exception, we coalesce it to a failing completion signature in the main operation state. We use our helper lambda to dispatch it, and then we return because the operation ended in error. On the other hand, if we succeed in gathering all of the values from all of the child states, we go to the central operation state and we request that it complete, that it take the vector stored in the result, if any, and send it down the value channel of our receiver. But this simply performs finalization once all of our children have arrived. We need to actually handle those completion signatures as they are arriving, and so we have a helper function for error and stopped completion signatures. Remember, we only want to store the first one, and so we go out and atomically determine whether or not we're first. But note that I use memory order relaxed here. I don't care about establishing an interthread happens before relationship. I just want to make sure that the action guarded by the if statement occurs exactly once. I don't care about the order in which those are published. All of that will be taken care of by the acquire release atomic fetch increment we saw before. Ben?
Isn't this equivalent to asking whether the stop source has been requested? Why are you keeping a separate atomic? Is it not somehow equivalent?
It's possible that we could implement it. I'm trying to, that would also fire if we had a request from
Sure,
downstream.
we had a request from downstream, yeah, but in that case, don't you want to? Would that matter?
Well, it would matter. So it would matter if downstream requested.
If the children ignored the stop request.
Yeah, so but if the downstream request stopped, right, then the first child, let's say that no one requested stop, right? So no one has stopped.
Right.
Everyone's running. Downstream request stop. Now self-stop requested is true, and we'll store nothing, ever. Right? Because we'll never get into this branch. We want to get into this branch at least exactly one time.
Okay, but if you're stopped, you don't need to store anything, do you?
Well, in this formulation, you do. You could coalesce. I have no value. I have at least one value not stored, and I don't have anything stored in the main operation state to stopped. But then you need to do a linear scan of all the children to determine whether or not you're going to send set stopped. Right? So you do like a partial gather, which would affect the code on the previous slide. You'd visit some of them, and then the one that reported stopped, you'd say, okay, now I need to report stopped because there's no value here and no value in the main operation state. Right? Whereas here, we just store this as a first-class citizen. We say, we got stopped, the whole thing is stopped, and then the error lambda we saw in the preceding slide will just eagerly report this without scanning the children.
Okay.
Once we get into this branch, on only the first arrival, we go and we request that all of our children stop so that we can end overall asynchronous execution as quickly as possible. Then we have another of these no-throw impulse songs and dances. We use those carefully calculated no except from the first part of the talk to determine whether or not arriving at our central storage can throw an exception. We then parameterize our lambda on that no except and have our lambda perform that operation. If you guess that the next slide is going to have an if context for that guards us storing the throwing completion signature, you would be exactly right because that is exactly what we do. Note that in any case, we call maybe complete because we've actually arrived as a child. We need to check to see if we're the last child and perform the appropriate finalization if we are. Which brings us to the public-facing part of the child state, which brings us to getEnd, which is one of the basis operations forwarded through by our receiver. Recall that the receiver synthesized by our base class forwards all the basis operations through to the parent because it's just a thin wrapper around us. To yield the environment we parameterize our children on, we use that environment type that substitutes in our stop token. We construct it with our stop source so we can vend out those stop tokens, and then we provide the environment of our receiver so that it can forward through all of the other queries made there against. Now that we've reviewed this particular function, we can go on and we can look at the constructor, and we finally have all of the context necessary to understand the requirement for statebase. Note that statebase is initialized first, which means the reference back to the parent operation state is bound first. Thereafter, we're going to construct child operation state by moving the sender thereinto. As we reviewed internally, that's going to connect that sender with the implementation detail receiver. But remember what we wrote in the constructor for our operation state? We interrogated that receiver as to its environment over and over and over again, and there's no reason to believe that connecting this sender with our receiver won't do exactly the same thing. But if it interrogates that receiver as to its environment, that's going to forward that call through to us. It's going to forward through to that getEnd function we saw on the preceding slide, and that runs through that self-reference to the main operation state twice. If we hadn't already bound that reference, that would be undefined behavior, thereby necessitating not just the existence of state base, but the fact that it is the first base class to be initialized. With this out of the way, we can review the remainder of the basis operations forwarded through to us. We have set value, which is called by our children when they complete successfully, and we have another no-throw impulse song and dance. We see whether or not we can store this completion without throwing exceptions, and then we have impl, which actually performs the storage. On the next slide, we of course use if const expr to determine whether or not we're going to emit a try catch or just call impl without trying to catch exceptions. If we catch an exception trying to store a value completion signature, we just coalesce it to an error completion signature parameterized by the appropriate exception. But remember that error or stopped internally calls may be complete, and so we return instead of allowing that to occur. If, on the other hand, we successfully stored the value completion signature, we go to the bottom of the function, we call maybe complete, and maybe we finalize the overall operation. Which just leaves set error and set stopped, which we already wrote helpers for, and so we simply call error or stopped with the appropriate tag type. With this code written, we've actually implemented all of the asynchronous execution of when all range. We've implemented the entire operation state, which is actually what implements that logic. But this doesn't really do us any good if we can't actually get an operation state. And the way we get an operation state is we connect a sender to a receiver, which means that at some point we're going to need to have a when all range sender. Unsurprisingly, the when all range sender simply contains the range, which is the curried argument to this asynchronous analog of a function. Then it has a nested sender concept, which just opts it into being a sender, and it has the needful constructor to populate that range. Moving on, we're going to have some nested type aliases whose form is familiar to people who've used C++23 deducing this. Given ourselves possibly CVREF qualified, we want to figure out what the possibly CVREF qualified version of the range we're storing is. Then extending from that, we want to interrogate our child senders as to the completion signatures they send with the CVREF qualification copied from ourselves. But this exposes us to the possibility that senders might be differentially connectable depending on their CVREF qualification, which is exactly true, which brings up a property of senders that I refer to as shottedness. We can have invocables in the synchronous domain that have ref-qualified function call operators. They may be invocable only as an R value, or they may also be invocable as an L value. If they're invocable as an R value, we can only invoke them one time because invocation thereof is consumptive. And the same property applies to senders. If a sender can be connected only as an R value, if connecting it consumes it, it can only be used to synthesize one instance of asynchronous computation, and so we say that it is single shot. If, on the other hand, it can be connected as an L value, it can be connected multiple times to form an infinite stream of asynchronous computation, and so we say that it's multi-shot. But that raises a question. If senders can have shottedness and we're writing a sender, what should the shottedness of our sender be? Which properties of ranges should we consult with to answer this question? And we know there are certain kinds of ranges that can only be traversed one time. We know that we traverse the range in order to connect, and therefore if we are wrapping a range that is no stronger than input, which doesn't offer the multipass guarantee, we are single shot. On the other hand, if we wrap a range that is forward or stronger, which provides the multipass guarantee, then we can be connected as many times as our user wants, and we are multi-shot. Which brings us to actually implementing the necessary code to reify this. Which brings us to implementing get completion signatures to advertise out the ways in which we can complete. But look at the constraints. In the constraints, we actually model what we saw on the preceding slide. If the constraints from the preceding slide are not modeled, we neglect to emit any completion signatures at all. Trying to call this function is ill-formed. If we are an R value, we will always emit completion signatures, but if we are an L value, we will only emit completion signatures if the wrapped range is forward or stronger. But I kind of lied to you when I said that, because it's not the case that if this constraint is unconditionally satisfied, we will emit completion signatures, because we also need to be able to evaluate the return type of this function. And as we look to the trailing return type of this function, we see more reflection shenanigans. we see another splice. So let's look at this from the inside out. We see that we get a reflection of the completion signatures of our child. But once again, that's not a reflection of that type. That's a reflection of an alias to that type. And so we strip that off with the alias. Then we get a reflection of the environment with which this sender will be connected, and we pass it into our completion signatures function at const eval time. That implements all of the logic we saw at the very beginning of the talk. And it returns to us a reflection which we splice in to report our completion signatures. But that function doesn't always return our completion signatures. If we can't implement this operation, it throws an exception, and this fails to be a constant expression. We won't yield completion signatures in that case. Moving along, we need to actually, Ben.
You had stop source end of them there, is that right? Shouldn't that be just end?
No, because if it's end, that's going to be the environment from our consumer, which doesn't provide our custom stop token.
But you're connecting the outside sender, not the child senders.
But this completion signatures accepts the inner. So in reality, this doesn't actually matter.
Okay,
That went back and forth because the only thing that it interrogates that environment for is the allocator. And on the let's go back here. And here, where we actually interrogate the child, we provide the stop source end. So here it actually matters. Here it doesn't matter, but I provide the uniform overall environment just for consistency. Yeah. So moving on to actually connecting the sender and the receiver, we have a requires expression to check to see if the receiver can actually receive the completion signatures we emit. But this transitively requires us to get the completion signatures of ourselves. It requires we able to form a call to get completion signatures. And so this constraint transitively drags in all of the constraints we just reviewed on the preceding slide. Our shottedness requirements must be met, and we must be able to actually invoke completion signatures and not have it throw an exception at const eval time. The body of this function is, in some sense, not that interesting. We simply instantiate our operation state, construct it, and return it with cplusplus17 guaranteed RVO. Which brings us back to one of the first slides in the presentation, the sender factory, which actually produces when all range senders. And so we simply implement it with a perfunctory body. We simply construct the sender from the provided range. Which leads us to the question, why did we do all of this? We started out with A and B, and we were invoking them synchronously, and that just took too long. And then we composed them asynchronously, and that took the right amount of time. But then I threw out there that maybe we want to have a variable number of children. So what if we want to, for example, print a variable number of letters of the alphabet? What if we have iota pumped into transform? Transform takes and gets a sender that waits for U number of seconds. And it composes this with a then wrapper that writes out the appropriate letter of the alphabet. We can see at the top that we use a constant to parameterize this. We use the constant 6, but there's no reason we couldn't get this constant from user input, that it couldn't vary from run to run, that we couldn't output a variable number of letters of the alphabet. But given the program I'm showing you on screen, what happens if we actually run it? Does the code we spent the entire talk writing actually work? Of course. It just outputs the first 5 letters of the alphabet. But that's not that interesting. I could have done that with invoke all. Perhaps the most important thing is that it completes in 5 seconds. Which brings us to the end of the talk. Which brings us to the sleeper hit of the talk, which was reflection, which enabled us to write complicated template metaprogramming using normal C++ code, which enabled us, I'm pretty sure, to actually fit this talk in this time slot. But this isn't a reflection talk. This isn't stood execution talk. And so maybe the takeaway is that you now know how to implement when all range. But in some sense, when all range is not that interesting. When all range is just one possible asynchronous algorithm amidst an infinite field thereof. What we actually discovered throughout this talk is that stood execution is actually a generic basis for asynchronous computation. That you can enrich the basis set of operations shipping with C++26 with new generic algorithms. That the promise originally laid out by the STL and then extended in ranges now extends into the asynchronous domain through stood execution, which doesn't give you the power to write an asynchronous program. In some sense, it gives you the power to write any asynchronous program. Are there any questions? Matt.
Can you go back to the summary? Leave the summary slide up.
Okay, yeah. Matt.
So you have the integer that is the fetch add for all of your accounting things, and it's acquire release every time. I think, why is it acquire release and not simply acquire or relaxed or something when you're doing it, and then one release at the end when you've reached. I might have my release and my acquire backwards, but why not do half the memory orders when you're going up to it, and then once you've got n, do the other half to give it out to the people downstream of you.
I'm thinking about that, and I can't think about what that would look like. Like, it needs to be, because so when you do that operation, the way that it's reified right now is you're doing a release in case the next person reads the final value, right? So that you happen before them. And you're doing acquire in case you read the highest value, so you synchronize with everyone who's written values before you, right? If you did anything weaker, that synchronization would flow in only one way, and then operations could float across the atomic.
Yeah, I'm thinking of if you've got to the last value, you then do the stronger one to get it.
A stronger one, like you actually emit like a raw memory barrier, because you wouldn't be doing a write that anyone else would be synchronizing with, right? You'd be doing a write that you invent yourself.
I was thinking of doing another load on it. You do if you do releases on each of the increments, and then if you're the increment that got it to the big enough number, you do a load acquire.
Wait, but that would, hold on. I'm trying to think that if someone has an answer to that, I think what would happen there is that and someone who has read the wording of the memory ordering stuff more carefully than me can answer. If you do a release increment and you load a certain value, right? You wrote that value. And then if you do an acquire load on that value, you synchronize with yourself.
So it chains across the atomic read modify write.
So it would chain through the modification order of the variable.
Yeah.
Yeah, okay, so then I guess you could implement it that way. You could implement it as a load and then...
But the extra load doesn't actually help you, since, at least on x86, everything is acquire release.
Yeah, and x86, everything
so
is
you're just
acquire
doing an
release.
extra load for nothing.
Yeah, you're doing an extra load for... but then also would... I guess it doesn't matter whether you expect the value, right? The reads and stores synchronize just by virtue of the fact they read some value.
Yeah.
Right, so just emitting the load would be sufficient to synchronize. You don't have to actually even check the value as the same one that you wrote.
I believe that is the case.
Okay, then, I mean, I don't know if that would optimize or pessimize the atomic increments. I would be very interested to have a benchmark where I could even measure that atomic increment against the background noise of the operation.
You're going to need to not be on x86.
Okay. I'll whip out my non-x86.
It sounds
CPU.
like a risky optimization. The benefit would probably be very small, and it takes serious analysis to know if it actually is safe.
Yeah, and that's what's pointed on x86. It might pessimize by one load.
Do you have a Mac there?
I do.
There's your non-x86 machine.
If it's new enough.
If it's, yeah. Any other questions? Okay, well, thank you all for coming.